So in this section, skipping way ahead now to chapter 8, talking about three big concepts: simplifying, multiplying, and dividing rational expressions. And by rational expressions, all I really mean is a fraction, essentially. Um, a fraction usually with variables, right? Things like x over x plus 2. Right now we have, it looks like a fraction. It's just got some bigger things, scarier looking things in it. But I assure you, everything you learned about fractions apply here also. So if we want to start just by talking about simplifying rational expressions, making them easier to work with, we have one simple property, and that's if I have some kind of a common factor, right? Like I've got my c's in common here, right? They cancel out. They go away. So this is equal to a over b. Maybe I'll keep my color scheme the same here. All right, with of course the catch that I can't divide by 0, so just as long as I'm not dividing by 0, I'm good. For our intents and purposes, this is just us being formal. But if you were to kind of move on, even move up to like an honors level, this would become more important. So my example is 15 over 65. No, you cannot just cancel out the 5s. But both of these terms share a common factor. It's not the color I wanted. Share a common factor of 5, right? This is 3 times 5, and then 65 is 13 times 5. So my 5s cancel out, and I'm left with 3 over 13, and this is in simplest form. I can't reduce that anymore, right? This is what we learned with fractions. This is just reducing fractions. If I extend this now to variables, to like fully rational functions here, kind of my big thing here, it doesn't look like there's a common term, at least not right away, but I've got this quadratic here, and what I can do with quadratics, of course, is factor. So we're going to do that. I'm looking for factors of 15 that add up to 2 to negative 2, so that would be x plus 3 and x minus 5. And of course, there it is, right? There's my common factor of x plus 3. It goes away, and I'm left with 4 over x minus 5. I'm really just reducing fractions, right? All I'm really doing is reducing fractions. Let's see this in action a couple more times. If I look on the right here, x squared minus 2x minus 15 over x squared minus 9. Well, now I've got two quadratics that I need to work with, and we've learned that the first one factors into x plus 3x minus 5. We just did that. And kind of my thought process is if I'm looking at what I have here on the numerator, can I factor x squared minus 9 into something that would allow me to cancel out a common factor? And yes, I can, right? This is, of course, a difference of squares. So this is going to be x plus 3, x minus 3. Of course, my x plus 3's cancel out again, and I'm left with x minus 5 over x minus 3, and that's totally okay. That's exactly how it should look. So likewise over here, right? We'll deal with the numbers later, the 2 and the 6 later, but my numerator doesn't factor. But part of my denominator does. This is factors of 9 that add up to 6, or you might notice that it's a perfect square trinomial. But if you don't, you realize that this is x plus 3 times x plus 3, or x plus 3 squared. And we have a whole bunch of simplification we can do, right? One of my x plus 3's cancel out. Well, and 2 and 6 are also reducible by a factor of 2, right? So 2 would become 1, 6 would become 3, and my final answer then would be 1, right? Everything's canceled out on top, over 3 times x plus 3. And that's really all we're doing. And this is something that's going to come back over and over and over again as we're looking at these couple operations, and even as we move into the next lesson talking about addition and subtraction. I know that feels kind of backwards, but we really are starting with the easier piece. So we move on to kind of the building block of rational expressions, and it's multiplication. Highlight this. Multiplication. Everything I do here, everything I do with rational expressions is going to come back to multiplication in some form of operations with rational expressions, right? Everything I do is going to come back to multiplication in some form. So this is crucial, right? Multiplying rational expressions, I've got my property right here, right? I have a fraction a over b and a fraction c over d, and when I multiply them together, I just multiply across. All we're doing. So let's say multiply across. Of course, I can't divide by 0, like I said, so just to be formal, b and d cannot be 0, but not super crucial for us in this class. The crucial piece is right here. And of course, I didn't show it here, but we learned how to do this when we talked about fractions, right? Think way back, 1/2 times 3/5 is 3 over 10, right? I just multiply across. 1 times 3 is 3, 2 times 5 is 10. So likewise here, right? If I've got this disaster, it's kind of messy looking, but it's okay. I have 5x squared over 2xy squared times 6xy cubed divided by 10y, and it looks overwhelming, but we're just going to multiply across. So 5 times 6 is 30. X squared times x is x cubed, and my y cubed. Likewise, on the denominator, 2 times 10 is 20, x, y cubed. And now we're going to simplify. So the big key is always simplify. I'm going to come back to that in a minute, but always simplify. So 30 and 20 are reducible by 10, right? So this becomes a 3 and a 2. I have my x's. My laws of exponents tells me that if I'm dividing the same base, I subtract the power. So 3 minus 1 is 2. And then my y cubes both cancel out. 3 minus 3 is 0. So if I were to kind of show all of that canceling out, which maybe I'm not the biggest fan of because it does make it look a little bit messier, but my final answer is actually right here, 3x squared over 2. So in this version of the problem, I chose to simplify last. Do all my multiplication and simplify last. I personally don't like doing it that way. I like to simplify first. So this is the way that I would do it. I would look at each fraction on its own. I'd say, all right, I look at my first fraction. The x squared and the x, the power will reduce. So I have an x goes away here, and x goes away here. Not the best symbol, I guess. Nothing else happens. That's fine. And then over here, I see, well, the y cubed and the y will cancel. We'll reduce the power, so this would become a 2. This would go away. The 6 and the 10 are reducible by 2, so this is a 3 and a 5. And now we're kind of good to go. So I'm going to multiply across. So I'm going to get 3 times 5 is 15, x squared, y squared, and then 10 y squared on the bottom, just multiplying across, right? The only drawback of this is I do have to simplify again, right? So my y squareds will cancel. The 10 and the 15 are both divisible by 5. So I do get the same thing. Kind of whatever works. I kind of go for whatever I see first in reality. If I can simplify whatever I can beforehand, I will. But if I don't notice it, then I'll just do it at the end. Just keeping in mind that sometimes it can get a little bit messy to simplify all at the end because there's a lot going on. So I kind of like to simplify first and then check later at the end. But let's see this in action a couple different ways. So this first problem looks just like the ones that we just covered. I'm going to do it this time the simplify last way, just so we can kind of think about a clear process of one step and then the next. So my first step is just to multiply across. So 8 times 7 is 56. The x's will combine. Actually, before even doing it that way, instead of doing it that way, let's actually write it out in full. 8x cubed y times 7x fourth y cubed on the top. And then we have 2xy squared and then 4y on the bottom in the denominator. So kind of going to simplify this, I'm just going to move on to the next page down here. 8 times 7 is 56. My laws of exponents allow me to add powers, so x to the 7th and y to the 4th. In the denominator, 2 times 4 is 8, x, and then y cubed. So that was kind of my first step, right? Multiply. And now I need to simplify. So let's see, 56 divided by 8 is 7, so this reduces to a 7 and a 1. Okay, just keep my fraction bar here to stay organized. Laws of exponents tell me division of powers I subtract. So 7 minus 1 is 6, so x to the 6th. And then 4 minus 3 is 1, so just a y on the top. Everything kind of came out of the denominator here, so we're left with just over 1, which you can kind of just ignore. Right? So multiply and then simplify. If we see this one more time, now we're starting to throw in some polynomials. And when I do that, before I even multiply, so maybe I'll call it like step 0, I want to factor before I do anything else. Maybe I'll change my colors, try to keep my color scheme the same. Right, before I do anything else, I want to factor first. Common terms, trinomials to binomials, whatever I can. So I notice in this first term, in this, the first numerator here, there's a 3x in common. And when I factor that out, well, I've pulled all of the 3x out of the 3x, so I'm left with just a 1 in my first term. And then I've pulled the 3 out, I've pulled 1x out, so I'm left with just 1x. In the denominator of the first term, I'm looking for factors of 5 that add up to 4, and that negative, of course, at the end tells me I'm looking for different signs. So that's going to be x plus 5, x minus 1. In our second numerator, factors of 20 that add up to 1, it's going to be positive 5 and negative 4. And then my 3x, fortunately, does not simplify. Great. So now we've factored, now we can multiply. And by multiplying, I mean basically just write everything next to each other, right? So let me move down here. So I have 3x, 1 minus x plus 5, x minus 4. And then in the denominator, I have x plus 5, x minus 1, and 3x. Oops, colors. So let's simplify. All right, so I see an x plus 5 in common. I see a 3x in common. Those can cancel out, and I'm kind of intrigued by this 1 minus x and this x minus 1. They look very similar. And the truth is, when they're essentially what happens is when they're similar like this, they cancel as long as there's a negative 1 left over. So we're going to actually go through and cancel this out. But making a note that when I do that, I need to be left with a negative 1. So if the terms are flipped in subtraction, I can cancel out. I just need to make sure I have a negative 1 left over. So in simplifying, I've kind of canceled everything out, right? Except for this negative x minus 4. That's multiplication. Division is going to work very much the same way. Division is going to be very similar. With one added step. So our property for division, oops, I want to highlight first. Our property for division is to rewrite it in terms of multiplication, which then, as we know, we're just multiplying across. So division of rational expressions is the same as multiplication by what we call the reciprocal, which means I've basically just flipped the fraction over, right? You see c plus d, c over d, and you see its reciprocal, not a good color to use. You see its reciprocal, d over c, there. So these are reciprocals of each other. Right? I just have spelling. Spelling is not my thing. Reciprocal. These are reciprocals of each other. I've just flipped it over. Some teachers, so when you first learned how to divide fractions, you might have heard the phrase keep, change, flip. Right? Keep the first fraction, right? Keep the first fraction. Change the sign from division to multiplication, and then flip the second fraction over. Well, then it just becomes multiplication, and I'm just going to multiply across. And of course, to be formal, I just want to make sure I'm never dividing by 0 anywhere in the problem. So, like I said, with fractions, right, if I were to learn how to do this with fractions, just normal fractions, my first step would be to keep, change, flip. And then multiply. And this doesn't reduce, so this is already in simplest terms, which is great. Likewise with rational expressions, I'm going to keep, change, flip, and multiply across. This is 7 times 2x minus 3, x plus 1, x plus 2. I've got nothing in common, so I know I'm good to go. My answer is there. Like, my answer is good to go. My answer is done. So let's check out 2 more examples. Little practice never hurt, right? So the same principles apply. I want to make sure I factor before I do anything else, and I want to make sure I simplify when I'm done. So let's factor first. There's a common factor of 2 in my first denominator. There's a common factor of x in my second numerator, and there's, well, I'm looking for factors of 30 that add up to negative 11. It's going to be minus 5 and minus 6. Okay, so then we're going to keep, change, flip, and multiply across, right? This is just going to be 7x, x minus 5, x minus 6. So we're just kind of stringing everything all together, right? 2, x minus 5, x minus 6. All right, so if we're walking through my steps here, I factored. We keep, change, flip. We multiply. And now we simplify. So I see an x in common. I see an x minus 5, and I see an x minus 6. Wow. And all you're left with is 7 over 2. That worked out nice. So those are my 4 steps, right? Factor if I have to. So kind of just if possible. Keep, change, flip on division. And now it's just a multiplication problem. We've learned how to do multiplication problems. Keep, change, flip, multiply, simplify. Let's try it one more time. Over here on my right-hand side, one just quick thing to note is, of course, any whole number, right? 2 can be written as 2 over 1. Same thing is true as a polynomial, right? This is like saying 3x squared plus 5x all over 1. And it's helpful in division to think about it that way. So factor if possible. I cannot think of any factors of 6 times 15 offhand that add up to negative add up to positive 1. So we're going to hold off and come back to it. Maybe I'll try to factor that later, but I don't think, kind of off the top of my head, that it factors that way. So let's kind of leave this alone. 4x squared obviously doesn't factor. But 3x squared plus 5x has a common factor of x. That leaves me with 3x plus 5. So we're going to keep, change, flip, 3 squared. And multiply. So we have 6x squared plus x minus 15. X squared times x is x cubed. And I got this 3x plus 5. It's really throwing me for a loop here. So you know what? Let's be safe and let's check and make sure that our numerator does not simplify. So we get 1 and 90, 2 and 45, 3 and 30, 4 doesn't work, 5 and 18, 6 and 15, 7, 8, 9 and 10, 9 and 10. 9 and 10 do work. So we've got some work to do. I'm going to kind of do this off to the side because I think it's messy to just keep carrying down the denominator. So 6x squared plus x minus 15. We're going to factor by grouping. So we're going to write this as minus 9x plus 10x so we can get our plus 1. Right, so I've expanded my middle term. We're going to group off, of course. So I get 3x, oh yeah, there it is. X minus 3 plus 2. Oh no, nope. Sorry, it should be 2x minus 3. 5 times 2x minus 3, factoring out my common factors. So we get 3x plus 5, 2x minus 3, and sure enough, whoa, sure enough, this does actually factor. So I don't assume like I did. Don't ever assume. Please actually do the work and check. Don't be lazy like me. So our numerator becomes 3x plus 5 times 2x minus 3. Our denominator stays the same, but it does simplify. 2, 3x plus 5, so that can go away. And I'm left with 2x minus 3 over 4x cubed. So kind of really quickly, the key here is you kind of see this layering, right? Division kind of involves everything, right? Division involves multiplication and then simplification. Right, we learned how to multiply, right? If we took a step backwards, we just multiplied first. And multiplication, of course, came with the added step of we need to simplify too. So we started with simplifying. So everything here kind of tiers and builds up. So there's a real nice natural progression from the start to the finish of this unit, which I think makes it very helpful to learn how to connect from point A to point B to point C.